great to be back here at the IFR. Today, I'm going to be speaking about some stuff about which, it's work in progress, and some things I'm a bit confused about. So I thought, what's better than to speak at the IFR and try and, alleviate some of the confusions. So we are going to be speaking about, I'm going to be telling you about BMS field theories. So this is a brief outline of the talk. So we are going to, what I've been trying to do over the last few years is trying to understand if there's a notion of holography for flat spacetimes. And I'll give you a brief outline of what the philosophy behind this is. Then I will be going to say something about BDC black holes and what we can do about taking flash limits on the BDC black holes. And we will be trying to, again, look at the dual theory and the notion of modular invariance in the dual theory to derive what we call a BMS, BMS version of the Cardy formula. So this is all past work, but I just wanted to give you an idea of where we were going before I go on to newer stuff. So I'll then be focusing on the recent work that we are trying to do, and we will be trying to understand the construction of characters in the highest weight representations of the BMS. And we will see that we can do it so that there are some things which had escaped me earlier, but we have been able to sort of sort some of these things out. So we would be able to get this in an intrinsic way from just symmetries and so on, and then we'll also be able to reproduce these same answers by looking at the flat limit from the if you wish, the ADS example. And there are some confusions which I would like to mainly focus on. And we've got certain answers. They look fine, but hidden there are some issues which I'd like to talk about and focus on as well, and try and see if you guys have any answers for me.
It would be a nice section title in a paper, confusions and solutions.
Yeah, I am going to write this in a very provocative way and see what responses I get. But it includes, as we go along, we will see there are more beasts lurking around the corner, and one of the ways to go about life is sort of try and hide your beasts somewhere. But what best than to try and share the beasts around. All right, so this is the. I don't know. I conclude that I have confusions, or the other way around. Let's see how it plays out. All right. So I have to conclude at some point of time. So I guess for the best interests of me and my audience, I have to stop somewhere. All right. So moving on. So what I want to do? Okay, I should be pointing at this here. So what is a recipe for holography? So we'll start off with a gravitational theory in a certain space-time dimension, in a certain space-time. What we'll do is we'll compute this. It's asymptotic symmetries. So for example, this the asymptotic symmetry group, for example, is the set of allowed diffeomorphisms modded out by the trivial diffeomorphisms. So what happens often is that the asymptotic symmetries turn out to be just the isometry of the vacuum, but there are famous exceptions. For example, when you're looking at ADS3, you end up with two copies of the Virasoro algebra. And that's sort of, you could say that analysis of Brown and Hanot is sort of like the birth of ADS-CFT, if you will. So we are going to declare that this asymptotic symmetry group is going to be the symmetry group of the dual field theory which lives on the boundary of space-time. And this is how we are going to build it. As I said, the prototypical example here is the Brown-Henner construction in ADS3. Later people have also looked at high spin holography in ADS3 in a very similar way. And for example, if you're looking to restrict to spin 3, then you get that your asymptotic symmetries are other W3 algebra, and you can try and construct the notion of a boundary theory, which is WCFT. So can we have similar? Can we have a similar lesson for flat spacetime? So what we are going to be doing is that we are going to be looking at symmetries of flat spacetime at null infinity, scri plus and scri minus. So these asymptotic symmetries of flat spacetime at null infinity is given by the so-called Born-Metzner-Sachs group. There's also in 3 and 4 dimensions, the BMS group is infinite dimensional. Whether or not it is infinite dimensional in higher dimensions is something which is a bit more subtle. You can restrict your boundary conditions such that you can get the Poincare group as the symmetries in the higher dimension. But whether or not you should use such strict boundary conditions is a matter of choice and of debate in the literatures. What we're going to be doing is so in 3 and 4 dimensions, you really do not have a choice. The BMS group is actually infinite dimensional. So what we will be doing is we're going to be focusing in the 3-dimensional case. And here, these asymptotic symmetries are given by the BMS-3 algebra, given by a structure of this kind. So you see there are these L's and these M's. So these M's are called supertranslations. So what are these supertranslations? Supertranslations are translations along, say, scri plus, which also depend on the circle at infinity. So these are going to be angle-dependent translations along the null direction. And these L's are the super rotations. These are just the diffeos of this circle at infinity. So Varnish and compare also looked at if you had Einstein theory in the bulk, then you could add 2 central extensions to this. One of them, CL, is 0, and CM turns out to be 3 over G. So this is work by Glenn Varnish and compare all the way back in 2006. All right, so that's BMS. So what can you do with, so one sort of, so you can, one sort of very straightforward, if you will, a way to understand flat space is by taking the radius of ADS out to infinity. So what you can do is you can also look at this at the level of the symmetry algebra. So at the level of the symmetry algebra, what happens is you can start off with 2 copies of the Virasoro algebra that form the asymptotic symmetries of ADS3. And in terms, so you also have, this is the Brown-Henner central charge, 3L over 2G. And we can take this following limit, which has L going to, L plus L bar. You notice the signs out here as well. And M's going to L plus an L bar. This is a minus L bar. And where this epsilon is G over L, and this goes to 0. So when you take this, you are actually this is easy to see that it just contracts these 2 copies of the Virasoro algebra to the BMS-3 algebra. The C's are, as I wrote down here, CL is C minus a C bar, and CM is epsilon times C plus a C bar. So one thing that you'll notice, this is something that I should have actually cleared up in the previous slide, which I did not do. So you see that these guys have a factor of G downstairs, and I do not have a factor of G downstairs. So you can scale this. You can take epsilon as 1 over L, And that gives you CM as 3 over G and matches up with the previous analysis that you had. Yeah, so that's a good point. The point essentially is that what you have here, I mean, this is a scale that you have to, I mean, put into the problem, and you need to take that out to 0. So that's how this is sort of like a singular change of basis. Now you could ask me that, you know, here it seems to be fine because I have 2 length scales in the game, and I'm taking a dimensionless guy out to 0. So that's sort of the more proper thing to do. Previously, I had a G there. If I had a G, if I were to just have an epsilon which looks, I mean, if this is like 1 over L instead of G over L, in that case, my central charge Cm is going to be 3 by G. Now you're going to say that this is a dimension sitting here, and it's a dimension full central charge. What does that really mean? What is going to happen as you go ahead when we are going to label states? The states are going to have weights as well. So if you have something that is going to be labeled by the super translation generators, which we will have, those states will also have this factor of G there. So what is important is actually the ratio of the central charge with the weight, and not the central charge or the weight, I mean, individually. So that's going to be the one that is going to appear, I mean, everywhere. But this is something to just keep in mind.
So there is a limit of Virasana cross Virasana.
Yeah.
Like this, in which the central charges are set to infinity, and then there is some. I'm just saying, just from the point of view of the field theory.
Yes.
So you know, Virasana cross Virasana.
That's right.
C and C bar to infinity, and then you say that there is a scaling limit.
Yes.
Of such an algebra.
Yes. Back to this algebra, which gives you this algebra.
And then is there something like the representation theory
Exactly.
works out all right?
That's what I'm going to be, I mean, going into actually. So I'll show you how we are going to be doing the representation theory out here. So this is the limit from ADS to flat space. Before I go ahead, so you know, as I said, my recipe for I mean holography in flat space will be that there is a field theory which is 2-dimensional that sits on scri plus and scri minus, and has these symmetries. So this is what I'm going to be using as input. So before I go there, let me try and you know, sort out a small something small, and then we will see that you can actually use this field theory to do something. You can actually compute something in the field theory which reproduces something in flat space. So let me just get to that.
In terms of soft theory, is it that the group quantity is soft theory in the above?
So we are speaking in terms of 3 dimensions, Einstein gravity. So you know there are no propagating degrees of freedom.
This is the symmetric group of the boundary, right?
That's right. But if you this is the symmetric group of the boundary theory when you're speaking in 3-dimensional flat spacetimes and 2-dimensional boundary theories. So what you want to reproduce is the symmetries of are things which will be of interest in 3-dimensional Einstein gravity.
So let's put some probe particles inside bulb.
Yes.
And talk about real scattering amplitudes.
Yes. So that you're already going a very far distance. So right now what I'm going to say, what I'm going to be interested in is just pure Einstein gravity. We are not going to put probes into, so this, I could go on speaking about this for weeks, but the thing that I want to focus on right now is a very small chunk of it. To answer what you are asking me, this is something that we wish to address, but we have not yet been able to address. So we would want to address what soft theorems would mean from the boundary field theory point of view if we can get word identities on the boundary field theory to reproduce this. But as you said, in order to do that, I need to put some matter into the game. And that'll require more than just just my asymptotic symmetries. I need to give you a way to, I need to give you a prescription of how you're going to match boundary things, say 2, 3, 4-point functions into things you do in the bulk. So some of it is stuff that people have done. A lot of it is work that is in progress. Another thing that I would like to stress is what I would be speaking today of is essentially, so you have scribe plus and scribe minus, okay? So scribe plus, scribe minus. I'm going to be dealing with a field theory that lives on one of the boundaries, okay? So I'm going to be restricting my attention to one field theory that, say, lives here, okay? In order to speak about S matrices, in order to speak about any sort of scattering amplitude in the bulk, I would need to say how scribe plus and scribe minus are linked to each other. This, from the point of view of the dual theory as we are trying to push it, we have not been able to do as yet. So I'm not giving you a prescription for all of flat holography. I'm saying that there are some aspects of flat holography that you can reproduce if you were to think of a field theory that lives on squares.
Is your expectation that it will be analogous to the case of 4 dimensions, where like common vector will be the diagonal of 2 copies of the
That's right. So there has actually been a little bit of work where people have looked at the three-dimensional version as well after Andy's done all these things. So there is a notion of how you should glue these two things together, and a notion of diagonal BMS as well. But we have not been able to we have not really tried to translate that into these questions of scattering matrices yet from just the perspective of a field theory that lives on the null boundary. But as you see, there'll be a lot of trouble just try to extract little bits of information here.
So now you will not be
I will in the first part, a little bit of stuff I'll be trying to do intrinsically, in the sense that I'll not speak about any limit from ADS. But I'll also try and see what answers I get, and if I can reproduce the same answers via these singular limits. So that's what I want to do. Again, as I go ahead, I'll say that these, some parts of it can be understood as a limit. Some of them are a little harder to do so. Okay, so moving on. So as I was saying, so the sort of road to flat holography, what we have been trying to push is that the field theory dual should inherit the asymptotic symmetries of flat space. So in three-dimensional Minkowski space, this dual theory should be a 2D field theory that lives on the null boundary of flat space, and it should have BMS-3 as its underlying algebra. As I said again, we are going to have two separate tools to study these field theories. One would be the intrinsic way, so we'll use only symmetries of the BMS, and the other would be the limiting way, so we will use a singular limit from the 2D CFTs. And yeah, so I've said all of this already, so we'll be attempting to understand aspects of flat space from field theory which lives only on scribe plus. This only gives a partial understanding of Minkowski holography. In order to get the entire picture, one will need to patch up these two field theories which live on these two null boundaries. All right, so moving ahead, yes.
The stuff that you would have in the bulk, which is not just gravity itself,
Mm-hmm.
but if there were other
Mm-hmm.
fields, then they would transform, so they would be the representation of this.
Yes, yes.
And they would be non-trivial representation, or trivial?
So that would depend on, so you would be able to, okay. So you could, for example, look at some field theory which is sort of like a scalar field theory, for example, and that would, you can find that I mean, if you wrote down equations of motion for those field theories, you would be able to see that they would be, I mean, invariant under, I mean, transformations of, I mean, of the BMS kind.
So let's say
So-
we talk about the operators that would be,
Yes.
would be dual to the
Yes,
set
yes.
C,
Yes,
then the correlation functions of those operators would be constrained by this symmetry?
yes, yes, yes,
Because I mean, when people talk about the soft theorems,
yes.
the only thing that they seem to constrain are soft elements.
That's right. That's right.
Not hard ones.
That is right. That is right.
That's specific to a higher dimension.
So again, this is, I mean, this is where I'll be just, I mean, using words because we have not really done that analysis.
No,
But I would assume that it would sort of have a similar role to play. I mean, you would be able to get, so I mean, if you should be able to get the symmetries of the S matrix, the full S matrix, I mean, out of, I mean, some ward identities that you have in the boundary theory. So yeah, so but again, this is expectations. All right, so moving on, let's address a rather interesting question that we did a few years back. So let's look at, for example, the BDZ black hole in 3 dimensions. And suppose we were to, so you know, if you take a limit on just global ADS goes to flat space, everything is fine. So what happens if you take the limit on the BDZ black hole? Now, here you're faced with some sort of a very weird situation in the sense that you have a theorem saying that in 3 dimensions, in flat space, there are no black holes. Now, what is really happening? I mean, why do you start off in ADS with something which was a black hole, took a limit, and then you do not get a black hole? How does this play out? So in order to do that, let's start off with a non-extremal black hole, non-extremal BDZ. Here the R plus and R minus are the outer and inner horizons. These are given in terms of the mass and angular momentum. Now we take L out to infinity. If you take L out to infinity, what happens is that the outer radius of the BDZ black hole actually goes out to infinity. But the inner radius does not. It survives the limit. Okay? So what you're left with in the limit is actually just the inside of the black hole. So this is, so inside of the black hole, so your radial direction and your time directions are flipped. So what you have is something that is dependent on time, and that is these, I mean, what we call these FSCs, flat space cosmologies. So the BTC inner horizon, as I said, survives this limit and becomes a cosmological horizon. You could now associate an entropy to this by Bekenstein Hawking, and this turns out to be, you know, this expression of pi j by root 2gn. So an interesting thing to look at out here is this work by Glenn and people in 2012, where they took, this is sort of the phase space, if you will. So you see that this angle, which was the Lm equal to plus minus j, so this just will flatten out, and you're going to get these cosmological solutions here where you used to have your regular BTCs.
Sorry?
Yeah, sure. No, all I'm doing is I'm holding the rest of it fixed, and I'm just sending L, the radius of ADS, out to infinity. No, R minus, yeah, I mean, this is just, a little bit of algebra. You'll see that. Yeah, it's just, yeah, you just, take the square roots and do this, and you'll see that R minus actually survives the limit. Okay. So this is fun. And what you are going to see is, so now, so we have a notion of an entropy which is associated with these, flat space cosmology solutions. And obviously, you did not have thought about this as a limited, as well. So you could have thought about it purely in flat space. And in that case, this is flat space. So you know that BTZs are orbifolds of ADS3. In a very similar way, these guys are orbifolds of three-dimensional Minkowski spacetimes. And when you are orbifolding by boost and a translation. So these also go under the name of shifted boost orbitals. Okay, and the shift is important in order to get this R naught there. Very good. So now let's move on to the aspects of the dual theory. So as I said, the symmetries of this putative dual boundary theory is given by the BMS-3 algebra. We will work in what is called, this is sort of like a plain representation of the theory. And we are going to be labeling states. Yeah, sure. Yes.
The off-diagonal is going to 0 or infinity?
Which off-diagonal?
L plus L bar.
Okay, so let me just write this down for you. So Ln was Ln minus L bar minus n, and Mn was epsilon times Ln plus L bar minus n. So what is happening is actually if you do this, if you do Ln, so this is going to be, so let me just schematically write things down where I also keep the epsilons. So this is going to be Lm n plus n. Ln and Mn is going to be M n plus m. And MM, this is going to be epsilon squared into L. Oh?
Yeah, maybe somebody can tell us the light.
Oh, sorry, yeah. Hi, Loga. Oh, I didn't notice you were there. So this is the epsilon squared piece. Okay. So this is the thing that when you're doing this singular change of basis, that is the piece that goes to zero. So that's. So what we are going to be doing is we are going to be using highest weights, highest weight representations, and we are going to be we will have the notion of BMS primaries where ln's and mn's acting on this where n greater than 0 gives you 0. Yes.
What was the algebraic geometry for that? Was it algebraically?
Yes. So as I was saying, you can think of this as taking a flat limit on your BTC black hole, but you can think of this more intrinsically as well as just a solution in three-dimensional Einstein gravity with lambda equal to 0, and these actually arise as, you could think of this as, an orbifold of flat space where you're modding out by a boost and a translation. So you can think of all of this intrinsically in flat space without any reference to any limit at all.
So the outer horizon was what you call the cosmological horizon, right?
No, the outer horizon was the outer horizon of the BTZ. That actually went out to infinity. Okay, so the inner horizon is something that survived the limit. And as I said, this was, if you are looking at a black hole, if you are inside the outer horizon, your radial direction and time direction flip, and that sort of becomes so the inner horizon becomes if your whole space time is actually the inside of a black hole, so that means that it's a time evolving geometry, and that thing is going to be. Yeah.
You took the flat space limit. You define the flat space limit as this L going to.
That's right. Yes.
Now L, of course, is not a dimension.
Yeah, as I was saying here. So you should essentially be thinking of this as G over L going to infinity. If you think of this as L going to infinity, in that case you would also have, so the, as I'm going to be saying that we are going to be labeling these states under these boosts. I mean, say M0. So if you chose to have your epsilon as 1 over L, then your xi's will also come equipped with some g's in them. So, but as you will see, the quantity of interest at the end of the day is xi over Cm. So this G is not going to be the one that's going to create any issues.
You have null sets.
Yes, we do have null sets.
So what are the boundaries now? Unitarity bound, what are the corresponding?
We will get to unitarity in a little bit. So that is one of the demons, actually. Okay, but let's get there slowly. Okay. All right. So what I'm going to be doing is I'm going to be looking at representations that are built out of this by out of these primary operators by these strings of L's and M's. So you can actually do some more interesting things with it. You can actually have the L0 L plus minus 1, M0 M plus minus 1 actually fixes the forms of these 2 and 3 point functions. You can do much more. You can try and write down 4 point functions, blocks, and you can have bootstrap equations, and that's another whole week of talks. But yeah. Xi at the moment is positive. Here there is an ambiguity. So okay, let me just show you this, that if you look at the algebra, you see m goes to minus m is a symmetry of the algebra. Okay?
Small m.
This big M. Because this guy, up to flips of sign for Cm, this is a symmetry of the algebra. So the sign of xi is going to be related with Cm again, and xi can take. At this moment you're not restricted to anything. This is something that we'll speak about a little.
This comes
Yeah.
out of this algebra only after the limit.
No.
It's there.
Yeah, it is there. Yeah.
Oh, because that's the off diagonal. That's the off diagonal part, which is the spin.
Yeah, the spin or the boost. If you wish. Yeah.
So in usual story CFT, this sign of central charge is related to unitarity, and here you are saying sort of the same story, but the sign of Cm is sort of related to if it is going to decay or not.
We are going a little fast. Let's slow down a little, because you'll see that okay. So since you brought it up, what is going to happen is I'm going to say to you, well, I was going to say this much later, but let's put the demons out. The highest rate representations are explicitly non-unitary. You can actually see that. Okay. Now you would ask me that why do I bother at all? Why do I want to construct a dual to a theory of quantum gravity where I'm trying to work with representations that are non-unitary?
Unitary with what norm?
Unitary with what the usual norm, if you want. But just to
Standard ones also are not unitary. The standard, if you just take two copies of the answer,
yeah.
your favorite representation, the highest rate representation, that will contain
Yeah.
positive,
Yeah.
not positive, not violent unitary norm.
Yeah.
Not unitary in Euclidean sense.
Yeah. So you would.
Sorry, you want to take the Minkowski.
Yeah. Right. So you want things defined on your light cone. If you are to Euclideanize the light cone, there's so. Let me try and say why I am still working with this, even though I know that this is non-unitary. Now remember the things that you're asking me, in the sense that S matrix, okay? S matrix means that you have stuff going in through scri minus and stuff going out through scri plus. Let's suppose we are in dimensions which are greater than 3, where, or you have in three dimensions you have put some fields into it, right? Remember that I'm only giving you a field theory that lives on scri plus. I've not said anything about scri minus. So this is more or less like an open system in the sense that there's stuff going out through it all the time. So you would believe these are, now I'm going to wave hands. You would want to believe that a unitarity is something that you do not force on the system which is only on scri plus. You would want your system that a field theory that is living on scri plus, if you are looking at representations, you would not want it to be unitary to start off with. You would want unitarity to emerge when you are gluing together scri plus and scri minus. I'm speaking to you only about these theories that live on scri plus for the moment. You would ask me, how am I going to generate a unitary theory out of some representations which are non-unitary? The answer to that is I don't know yet. Second point is, the proof of the pudding is often in the eating, and we can actually do a lot with these sort of highest rate representations here, and we can match up things in the bulk, as I'll just show you. So there seems to be a very weird notion. These non-unitary, non-unitary representations seem to be very useful in this way. And to end up, this is where I should get to in a while, is that there is a very weird thing going on which I don't understand. There are some unitary representations, and there are these very useful non-unitary representations. But the answers of both of them seem to be very similar. That is something that I completely don't understand, but let's get to that at the end. Let's not just go out of hand right now. But before doing that, so what we are going to be doing is we want to understand the entropy of these flat space cosmologies that I just discussed. And I want to be doing this, and I want to be trying to understand the notion of modular invariance and in these BMS field theories. So first, in order to do that, I'm going to take these, move the theory from the plane onto the cylinder, if you wish, by this mapping.
Hello?
Yes.
Yeah, Arjun, I had a question.
Yeah, Lola.
About this cosmology.
Yes.
So just to make sure I understand, so this cosmology that you constructed by taking this L going to infinity.
Yes.
So which part of the DTG are you going up? Are you the cosmology that you're getting is a big crunch cosmology or a big bang cosmology?
So the cosmology that I'm getting is a Big Bang cosmology.
Okay, so you're basically blowing up the thing inside what we call fast particle.
So you're actually doing things such that you take the outer radius of the BTC out to infinity. So depending on where you are, if you are inside the the R naught, as I said, so it's big crunch or big bang depending on where you are. So if you are inside R naught, if you're inside the inner horizon, let's make sure that I get this right. If you're inside the inner horizon, then it's a big bang. But if you're outside it, then it's going to be a big crunch. Is that right? Yes, I think so. So the
it depends on which kind of
so let me draw this for you.
white hole or a black hole, right?
Yeah, so this is going to be the, you can take your usual, So yeah. So you take your usual Penrose diagram and you flip it. You flip it by flip it by a right angle.
In this will already appear in
Yeah.
the usual kind of diagram
Yes.
where the lower 45 degree line, the lowest
Yeah,
45
yeah,
degree
yeah,
line,
yes.
this will be the future outer horizon.
That's right. That's right. That's
and
right.
then the top 45 degree lines will
Yeah.
be the past outer horizon.
Yeah. So I mean, what I'm saying is that so you I mean, depending on where you are, it'll I mean either be a big bang or a big crunch.
And
Yeah.
solutions have finite charges as classical solutions?
Yes. Yes, they do. So there's this. So if you I mean if you're looking at Q of L naught, that is actually J, and Q of M naught is M. I mean GM if you wish. Okay?
Okay.
Yeah.
So phi is not real.
Phi is not real. What is phi?
X is into the alpha. You don't want X to be real or something.
Okay, so this is okay. All right. So I have compactified this. So it's like yeah. There's some factors of I. Yeah. So yeah. Maybe I've messed up with some factors of I somewhere. I this I'm not entirely sure of. So z is either the. So this is just plain to the cylinder, right?
So I don't think you mean X going to the power I or then your phi has to be complex. Yeah, phi is like the new complex derivative, right?
Yeah. Okay. So this is just this. So what I'm doing, I mean to get this, if you wish, is z is I mean either the I omega.
Right. Where
And-
Z is X plus IT.
Yes.
And omega is
Yeah.
tau plus I phi.
That's right. That's right.
That's what
And you expand things out. Yes.
yeah. So that wouldn't give this.
Yeah. I mean I've got some factors wrong maybe. Yeah. Yeah.
An automorphism will be definitely only after contraction, meaning the rotation of n by some phase.
The rotation of m by a phase is going to reflect on the central term as well. I mean, this is the thing, the discrete version of which the thing that I was trying to say, that m goes to minus m is is a symmetry of the
No,
classical
that-
algebra.
Yeah, that was present already. I'm trying to see if there is a new automorphism that appears after contraction. So what I'm interested
M-
in now is
Yeah.
comprehensive null states can also be thought of as limits of null states.
Yes.
But I was just interested in the new thing, and that would come about if you have something new happening.
Yeah. Unfortunately for the this particular algebra, I mean so for the I mean just the bosonic algebra, it does not seem that we are going to get any extra null states. But interestingly, some supersymmetric versions seem to have states that actually I mean degenerate in the limit. This is again going beyond what I want to say today. But the null state analysis for the bosonic case, you can do it in in the usual way. You can also try and take limits of your Gauss null states, and they just go through.
But you agree that m going to phase is the symmetry of this
What?
algebra, the automorphism algebra.
So you're saying mn goes to some number times m? Yes, it is.
Central charge also are
Central charges will be scaled up or down in the equivalent way. So you see that this particular thing, no, mm has mm is 0.
M is 0, right?
Mm is 0. Yes.
LM has a
LM also.
Yeah, LM has a central charge, so the linear thing just also goes into rescaling this central charge. Okay, so partition function for the theory that I want to write down is yeah.
LL also has a central term.
LL. Okay, so LL. Yeah. So
LL does not have a central term.
no. Okay, hold on. So the LL is L plus CL. LM is M plus CM, and MM is 0. Now, yeah, so if you are looking at Einstein gravity, then CL is also equal to 0. But you can look at, I mean, other theories, I mean, say, I mean, something like a topologically massive gravity, where you're going to get a CL. Okay. All right, so for the moment, we're going to keep CLs in the U. Okay, so you have, I mean, this ZBMS, which is the trace of, I mean, e to the L naught and e to the M naught now. And now you want to look at this as a limit from CFTs. Now, what are we trying to do is we will be trying to say that, you know, when you take this limit, the BMS, I mean, the partition function is going to emerge as you take, I mean, epsilon out to 0. So so the relation between the weights are that delta, which, so let me again clarify what delta is. So L naught acting on these states is delta, and M naught is xi with psi. So delta is h minus h bar, and xi is h plus h bar. I mean, epsilon times h plus h bar. So we take this limit, and then what we see is that if you have to keep this partition function, I mean, finite as I mean, epsilon goes to 0, you also need to scale these rows that I wrote down here by, I mean, to epsilon rho. Otherwise, these are going to blow up. As you see, there is a rho by epsilon out here.
The delta is like spin and the psi is like delta.
Okay. In this particular way of trying to map, I mean, map to representations, since you have a sign here,
Yeah, why did you put that sign there?
this is, I mean, because I wanted to go from, I mean, ADS to flat space, so the C was equal to C bar was equal to 3L by 2G, and I wanted to have CL equal to 0. So this is a limit that I put. What you're asking, there is going to be another limit where I actually flip the signs as well. I'll get, I mean, I'll, at some point of time, I'll also get to that. Okay, so. Yes.
You are taking the partition functions,
Yes.
rewriting them with respect to with your LNMs, new LNMs.
Yeah, L naught and M naught, yes.
And then you are taking this limit.
Yes, if I take the limit, I'm demanding that my partition function will not blow up. So you see, if I did not, so if I just wrote this in this basis, then I would have a rho by epsilon sitting here. Because xi, there is an epsilon which sits here. Okay? Because, yeah, so the xi was, so delta was h minus h bar, and xi was epsilon into h plus h bar. So when you replace, this epsilon is here because you have this epsilon here. Right? Oh, zeta is, all right. Zeta is just, I mean, the thing that you usually call tau. Yeah, so I mean, I think I must have used tau somewhere else. There you see there's a tau. So that is why I use zetas out here. But zeta is your usual CFT thing is this, right? Okay, so I've just put here. So you take your usual CFT partition function, write it down in its weights. sigma is imaginary, yes. Yes. So now what you're going to be doing is that you also need to scale rho as epsilon rho. Very good. So, yeah. So what is happening is that, sorry, yes, here. So if you write CFT,
So this torus is becoming small?
yes, yes,
Narrow?
yes, yes, yes.
But what? Not this necessarily I could have defined my theory or any, if it is really the field theory of the flat space that
Yes.
is describing the field
Yes.
bulk
Yes.
with Minkowski.
Yeah.
Symmetry, then in order to get a finite partition function, why do I need to take a scaling limit of my space?
No, I'm saying that your partition function is this. That
You are putting
that is
Z from there.
that is this Z.
You are putting extra epsilon.
No, hold on. This is this. Okay. I'm saying that when you start off with some Z CFT, and you put all of your epsilon in, and you take the epsilon going out to 0, my CFT partition function should go to my BMS partition function. So let's write down this CFT partition function. This in this basis, once I've done the trace, is going to look like this. Now what I do is I put h and h bar in terms of del times I.
Understand that you get an epsilon in the
Yes, yes.
But that's your problem now, right? I mean,
That's right, that's right.
Maybe there's getting the pixels and more. So what, this is something extra that you're doing, right? That the row also now you're saying needs to be scaled.
Let's see if this is right or not.
Okay.
Okay. So I'm saying that if I were to demand this, then things seem to work out. I mean, in the sense that this is going to be, if I were to identify things seem to be going through if I have this extra requirement of rho goes to epsilon rho. Okay. Suppose this were true.
That's probably just cancelling your scalings out and bringing you back to zero.
Yeah, if I didn't do it,
Yeah.
things will blow up. Okay. So so the partition function is like this. So there again, sort of, if you're looking at the Euclidean theory, then you have these two circles.
But sorry, this
Yeah.
partition function is the same as the CFT partition function, then, right? The incomplete
No.
delta, incomplete psi, that's what the CFT partition function was to begin with.
No, the CFT partition function, you'll see that it's not the same, right? Because you've done this extra thing. You've scaled the rho.
That's what I'm saying. That's what made it look like this CFT partition function. Before that, it was not.
No. It was all, so all I've done is this. Z BMS is trace e to the something 2 pi I sigma L naught e to the 2 pi I, what did I say, rho m naught. This is as it is, okay? Now I write Z CFT is equal to trace of e to the 2 pi I, what did I write? Anyway, tau L naught e to the minus 2 pi I tau L naught bar. Tau bar L naught bar. So what I'm saying is that if you had just rewritten Z, so what is happening is, in order to keep this thing finite at the end of the day, so the way that you are supposed to map these things as sigma is equal to, now, let me, sorry, what am I doing? So, yeah,
In this BMS Z,
yeah,
the row exponential has a minus sign or not?
rho exponential has some minus sign, no. I've just defined it in this way.
So then I don't understand how this is consistent with the first formula in the next page.
First formula in the next page. Why do you say so? Oh, there's a sign out there.
Yeah.
Okay.
Absolutely no sign.
Yeah. Okay. Yeah. I mean, okay. Now, if you're going to pin me down on signs, I'll be in trouble. But what is my convention? I think my convention is, so you see the reason why I have this extra sign out here is because I mean zeta and zeta bar, so these are I mean complex conjugates of each other, right?
No, I think either convention is okay, but
Yeah.
what is the convention?
Convention is hopefully what I've written down, in the sense that it's just, if you just substitute these here, you should just get. So you're saying that this is not consistent with the one I have up there, is it?
Well,
You may be
what
true.
conventions will- can
You may be right about the sign, but okay, so I'm not sure about this sign. Okay, there may be a sign mistake out here, but this is not an important sign. Okay, if you think it's an important sign, we can get back to it, but I think this is not an important sign.
So can you get back to the
Yeah.
technical argument?
Yes.
Okay,
So
we start off with something finite.
Right.
Finite
Right.
basis.
Yes.
And you from a singular thing with
Yes.
basis.
Yes.
And you have something that blows up.
Right.
And then you from another scaling to make it finite.
Yes.
Don't you get what you started off with?
That is the thing that I'm saying that you do not. So how do you see this?
I think the spectrum also gets changed. You're waiting for the same quantity, but the spectrum is going up and down.
So so the way you see this, for example, is suppose now, so the reason why I wanted to have this as a limit from a CFT is because I want to understand what the notion of, is there any remnant notion of modular invariance in my theory. Now let's just see this, okay. So if you were to write down the, I mean, what the modular transformation of the usual CFT is, this is just rho goes to a or what? Not rho. Zeta goes to a zeta plus b by c zeta plus d. You can write this down in this basis. So obviously here things have not changed. Okay. But now, if you were to scale, then your modular invariance in BMS is going to change. Okay. So what it has become now is you have one usual CFT-like thing and something that goes like this. Okay? So you can clearly see that this is not what you had. So it's not been rescaled back to your usual thing. It has changed stuff. Okay? So this is what we will call the BMS modular transformation. And depending on how much of time that I have, I mean, I have actually not even begun the part that I wanted to say today, which is how long do I have? You 45 minutes? Fantastic! Wow. Okay. All right. Very good. So I think I would be able to finish it. All right. So looking for something over? Escape. Yeah. Okay. So moving on. So what we want to do is we want to look at the invariance of the partition function under this transformation, and we are going to focus on the S transformation. So if we focus on the S transformation, so the thing that we are going to keep fixed is this Z naught, where you have these CLs and CMs which are factored out. Sure. Yes. Yeah. Uh-huh. Exactly. Oh God. Yeah. Precisely my point. I didn't want to make it because again, this is something that we noticed. So what we were trying to say that this was like, I mean, precisely like the thing that you're saying. It's a Jacobi form, where you're not looking at this, but the square root of this essentially. So I mean, square root of rho is sort of like a Jacobi form.
Right.
But that also has another, transformation, right? So there's the second one where z goes to z plus 1, the shift transformation. I don't know how to get the shift transformation to work. So if you guys have any idea about
If you take
the t, I mean actually the t just becomes rho goes to rho. So I mean the thing is,
He's not picking up the translation.
yeah. So just will wash that thing out.
Yeah, but that will get it.
That's why, I mean, you can expand this out. So there is a rho squared and so on. So the rho squared and the higher things just are down by factors of epsilon. So that gets washed out. So if there is a way that you guys can think that one can generate the other transformation, I'll be very happy to know that. Yes.
There is no extra shift transform.
Okay. Yes.
It's only a simple plane.
Yes.
Because that form is very simple.
Right. Right.
If we have extra chemical potential, then we would have a tau going to, well, z going to z plus lambda tau plus. Here somehow sigma and rho seem to come from tau and tau half.
Yes. Yes.
So the problem is if you don't expect to see, but if you want to say this is Jacobi form, then
That is why. I mean, you know, it sort of looks like it, but if you can give only one of the two transformations, it's not quite a Jacobi form anymore, right? But yeah. Okay, moving on. Yes. Yes, that is right. But that was a part of a talk, this talk that I was trying to give and trying to think about that I would write earlier, where I will try and speak about the modular bootstrap. But you know, seeing that I've not even begun what I wanted to say, it's good that I didn't think about trying to write that bit. But okay, anyway, so
Transformation rules do not preserve the nature of sigma. If you start with purely complex sigma, the definition of sigma was purely complex. The definition you use, tau minus tau 1, that's purely complex. Start with purely complex sigma, do this transformation. You end up with something else, unless you say something about ABCD.
no. No,
Can you just go back one slide?
Yeah, I could go back another slide.
So now you start with purely complex sigma.
Yes.
So if your B is not purely, so you're mixing, if ABCDs are real or not, that's the question I'm asking.
ABCDs are, this is the usual CFT transformation, right? So
They're real,
just,
right?
I mean, AD minus BC is
They're real.
equal to 1. Yeah, I mean, ABCD is yeah, I mean, these are integral.
So now you have so the above you have a purely complex quantity with an addition of a real number. So you know your resulting sigma is not purely complex in general. It is not true.
See, the thing is that if you were to be if you were looking at the usual CFT thing, right? If you had only one tau in the game,
Yes.
then this you can write as I beta, right?
Now beta is also complex. Tau is complex, beta is complex. Is it not true?
Beta is,
Are you talking about only rectangular torus or torus in general?
am I talking about a rectangular torus or torus in general?
This one is almost like a rectangular torus. At least before you do this transformation, because your rho was almost very small and sigma
No.
was
See.
smaller.
The thing is, let's. I mean, yeah. Sure.
Here, for example, you can take your torus to be rectangle to begin with.
Okay.
And then when you start with that, so your sigma has some reality property. That reality property is not preserved by this transformation is more than something like that.
Yeah, I mean,
So you need to make sense of it for complex sigma if you were to
yeah, probably. Okay, let's say this. So if you were to try and if you want your partition function at the end of the day to be real. Okay, so this is something that you're going to impose on it. so for example, if you're doing, so if you are trying to write down a partition function for I mean CFT to begin with, so it may not be, so it given in terms of the characters of the underlying Virasoro algebra, so these transform in a certain way, so this may not be explicitly real. So this is defined on some sort of, but if you were to try and understand how to impose things like how to impose modular invariance to restrict your spectrum, in that case you'll have to do it on a real slice.
So you are going to, at the end you will claim that ZBMS is a real number, is it?
If I were to look at how this sort of restricted form of a modular invariance is going to put bounds and stuff on my spectrum, in that case I will do that. So but that's something again that I'm not going to do here. But the thing that I'm trying to say is that if you were to come from a CFT point of view, the restricted form of the sort of modular transformation that you have is this. Yeah.
When we write down the partition function,
Yes.
tau and tau bar can be independent complexes.
Exactly.
In
So
this case, sigma and rho are independent.
that's right. So it's only when you try and put bounds on what your spectrum is that you demand that you're on a real slice, that tau and tau bar are actually the complex conjugates of each other, and then you go on to do these things. Yeah.
Shouldn't you write zeta as sigma plus rho by epsilon according to those definitions?
No, right now, yeah. So what I'm trying to say is that if you had not scaled these, then this is what this is just the thing that you would have got. Okay. Now I had demanded that your partition function should remain finite in the limit. That is why you need to scale these with epsilons here. You have to put an epsilon here. You need to put an epsilon here. You need to put an epsilon squared there.
And your tau written there.
Yeah. So this was the first step, and then tau zeta whatever. So then you do this. So it's a two-step process.
How we got that final.
All right.
So it's 2 steps. So I've done this first, then I've done this. That is why you have got rid of all the rho squared pieces. There's an epsilon squared here, but there's an epsilon here. So there's a relative factor of epsilon to all these higher terms, and they just drop off. Okay. So probably let me try and just push forward a little, because I really want to get to the new stuff where I've got nowhere near to it. So what I'm going to be doing is I'm going to be looking at the S transformation in BMS, which is of this sort now, and we are going to be looking at trying to understand how to derive Cardy like counting out of this. So if you do that, we use tricks similar to what's done for the usual CFTs. So you demand the invariance of the Z0, which is the partition function, but with these CLs and CMs just factored out. So once you do this, so you can write down Z BMS in terms of the S dual form, S transform form, and you get all of these extra factors out in front. All right. So once and then you can find what the what these density of states is through to an inverse Laplace transformation, and you can you can work at the limit of large central charges. What you get is when you put the value of the extremum in, so you end up with a formula which looks like this. As you see, there's always xi by CMs which sit here, You can do more with this, and you can try and find out what the next leading term is, and there's a log piece to it, and so on and so forth. Now we have a formula from the field theory point of view of what the entropy is, and obviously the thing that I'm going to be doing now is I'm going to be putting weights for the FSC in. So actually becomes GM by CM over 24.
That was the density of state with high energy?
Yes. Yes. So this is the usual. So if you are doing a usual Cardy like counting, but you have replaced the symmetry algebra with this new symmetry algebra, this is the thing that you get. So this is the BMS version. Yes. The large, large weights actually. So xi and delta are large. Now there would be a way to extrapolate this to other things which we are trying to do at the moment. But yeah. So for this is just yeah. So what we did is we demanded the S invariance. And we related, we said that the Z naught BMS, which is the Z BMS with this thing just factored out, is going to be invariant under the S transformations. Once you do that, you can find what the density of states is by an inverse Laplace transform. And you can look at this at the limit of, you can look at this integral at the limit of large xi and delta. Yeah. And that's right. Yeah.
So this is also taking appropriate factors to account for the ion due to the power of
yeah. So what we do is we demand, as I say, the invariance of Z naught. And then you write Z BMS in terms of the S transform Z BMS, and then so this D is just the inverse Laplace transform of this, and you want to now do a saddle point approximation and find out what the how to do this integral.
In doing that, you were just replacing that Z by 1.
You are replacing that you are saying that at the particular saddle point this is not going to be rapidly fluctuating, and you can just factor it out.
Large saddle point, because the subleading saddle points would be
will be down by factors of CM. Yeah.
I don't know which C it is.
Yeah. It will be the CM actually. So that's what you get.
How is the sigma integral done by development? Because the sigma integral is still coupled in
the sigma, no, the xi is here, right? So what you do is you are looking at large, large delta and large xi. So you, approximate, yeah. So you're just looking at, yeah. That's what I want. And then this is in this large approximation we have dropped a few terms, and then you can get the equivalent. So you can get the F max, and you can just do the integral, and then you get what your S naught is. So you get the BMS version of the Cardy formula, and this is so you can also look at its log. The next two leading pieces as well.
So the partial function just goes to 1 over?
Yeah, so that's something that that is you can check that at the saddle point it's not rapidly fluctuating, and then you it's not rapidly fluctuating at the saddle point. Classical value is not really, it's that particular thing is just going to give you some factor in front, right? So that won't be important. Okay, so yes.
Arjun,
Yeah.
what is the relation between these two formulas?
Hold on. It should not be. Okay. No. Sorry. Yeah. So, so this is something I wrote down later and maybe at the end. So treat your sigmas as xi's. This is all over the place. All right. Don't look at this. Okay. So I mean I should actually delete this. But let me write this down for you. This is atrocious. So let me just rewrite this for you. Thanks for pointing it out, Loga.
The box formula is correct.
Yeah, the box is right. The one downstairs is not, and the one which is right. So the S0 is fine. I mean the S0 is this one, and so it is 2 pi CL over. This is xi, okay? Xi is Cm plus this is this is delta. I mean, how I wrote this formula, maybe I was sleeping. I'm sorry about that. So there is a 2 somewhere else. Yeah, there's a 2 here. Yeah, there's a 2 downstairs. Yeah, so this is the leading piece, and the next piece is minus 3 over 2 log of twice xi by Cm to the third. Yeah. Yeah. Yeah.
Can you go back to the previous slide?
Sure.
If you're assuming certain things about the Z, right? When you do that one, that's not growing exponentially with sigma and so on. Whereas if it's delta and psi.
It's not growing exponentially with delta and psi. So I'm just I mean here what I'm trying to do is that here I'm saying that at the so this is so you can check when you're looking at the limit of large delta and psi, this z is not going to be rapidly I mean fluctuating. So your saddle point analysis I mean will hold good. So that's all I'm doing at the moment. All right, so very good. So what we have done is we have looked at something that is going to, so okay. So now what you can do is you can put, you know, I mean you can look at the weights for the flat space cosmology, and as expected, this is going to reproduce the answers which we have earlier. So this, you know, xi becomes, I mean 8, I mean gm plus. This 1 over 8, this is the piece which is sort of the value of xi when you're looking at the Minkowski vacuum, and delta is j. So what you get is you get a matching between the Bekenstein-Hawking entropy that you had in the bulk and this, I mean this, the analysis that we did in this dual field theory, and these two things match up. Okay, so that was supposed to be my introduction. So we have 10, so maybe I'll try and wrap up in the next 10 minutes. So this is work that we are trying to do at the moment. Yeah. Oh, okay, yeah.
So the stuff that you're doing in the bulk,
Yes,
you got some cosmology,
yes,
right?
yes.
On the other hand, I thought your idea was to get a Minkowski diamond.
Why? So okay.
Is this what you? Okay,
So
this contraction that you're doing in
Yes.
field theory is giving you a cosmology. It's
okay,
not-
so
it's
let's just step back. What I'm trying to say is that I mean in the usual sense, if you're looking at ADS, your dual is I mean if you're looking at ADS3, your dual is a CFT2, and the states in ADS are I mean also I mean would be your I mean states in your I mean dual two-dimensional CFT. So here you I mean you have so your BTC black holes are states in ADS. These are dual to I mean states in the two-dimensional CFT, and you can I mean count what the entropy of these BTC black holes is by an I mean by a Cardy-like counting in the dual theory. So there, what you do is you only use the symmetries of the dual field theory to get at that that equality. What I'm trying to say is that we have been able to reproduce a similar thing for these solutions in flat space, which are the equivalents of of the BDZ, if you will. So these are sort of like thermal states in your dual theory, and we've got a Cardy light counting to reproduce what the entropy is.
Yeah. My question was the BMS symmetry.
Yes.
I thought BMS symmetry applied to the just the Minkowski diamond.
It applies to all asymptotically flat. Yeah.
I see.
Yeah.
So in particular, the geometry that you have there
Yes.
is the flat space cosmology.
Yes. Yes.
With the time-like singularities and everything.
Yes. Yes.
there.
Yes. Yes. Okay. So.
This log term is 1 by theta. Log term is this large theta extension.
Log term is the leading thing. I mean, we did a saddle point analysis.
And then
Yeah.
Because
There's a
the
CM
other
there,
is
yeah,
1 over,
yeah.
1 over G.
Yeah.
1 over G is less.
Yeah.
So there's no,
Yeah. That's right.
Gravitational analysis already handles rockets.
We didn't. I mean, you would be able to do a one loop analysis to get this, but this is something that we did do actually.
But is that different universally? You would borrow it from another thing.
So the 3-half log is sort of, you get similar 3 halves in the CFT language. This is something that you could do actually. But it's just that this has not been properly done. But I don't expect that this is going to be a big issue. Yeah. Okay. So characters. So in the last, well, I don't know how many minutes, I'm going to be speaking about some work in progress with, an undergraduate actually. He is very, very good, Omar Shah, and Zoden, who's a postdoc at IIT Kanpur. And so let's just review what we know. So the Virasoro, highest weight characters are given by the trace of q to the L naught minus c over 24. By trace, we mean doing this. So you take these states h and h, highest weight states h, and this Lk essentially means this whole string of operators where you have L minus 1 to the K1 and minus 2 to the K2 and so on. So you can show that when you do this using this simple algebra and commutation relations, what you get is that you get c over q to the minus c over 24 outside, and the degeneracy of the number of states at a particular level into q to the n plus h. And so this is something that we want to also, this is a very similar thing that we want to do now for the case of the BMS. But before I do that, I'll just take a minute or two to just emphasize something that we didn't think about earlier. So what is it to take a trace? So let's take a linear operator O, and so the trace is the sum of its eigenvalues. Now we're going to take size as a set of linearly independent unimodular, but not orthogonal basis vectors. And we are going to take alpha I, which is going to be a set of orthonormal basis vectors. Now, if you look at a linear transformation between size and alphas, this is given by U. And as it's clear, this is what we try to do. So alpha I, alpha j is delta ij. This is 1, but this one is not equal to 0. So very clearly, if you take psi I with psi j, it just clearly says that U is not not going to be a unitary transformation. So what does what does taking a trace mean? So taking a trace means that you have you're going to do this sum. right? And we have taken these alpha as unity. So this is again the sum of its eigenvalues. So this is what we want. But suppose we want to do this in the non-orthogonal basis. In that case, the trace is alpha I, u dagger, O, u, and alpha I. Now what you can do is you can put identities in, and you can see that the trace prime is not the trace. Okay? So when you are looking at something, when you are looking at a set of linearly independent but not orthogonal basis vectors, your trace is not something that you are going to be defining with these psi's. Okay? But the Virasoro case, we do not use orthogonal states. So what's going on? Now let's look at the effect of degeneracy, which is the exception that proves the rule. So now you can look at let's look at a Hermitian operator. Again, psi I. Yes.
Sorry, what is the so we just take it as an inverse matrix, right? Like what we do in the Minkowski case. We put an inverse matrix and then take. Is that all that it is?
I'm just saying that you need to sort of, if you were to look at a basis, you just for an arbitrary operator A, you need
like
to
if
make
you take a trace.
Yes.
Sorry, if you take a trace of a tensor like say in some general coordinate.
Yes.
You put like G upper mu T down mu, right? So
That's right.
So we know how to take trace in a non-orthogonal basis. We just have to put an inverse matrix component.
That is right. So you just need to diagonalize your set. Orthogonalize your set.
You don't have to, but you just can. If you know the matrix, you can take the inverse and take it.
Sure. Yeah.
Do you know the matrix in this basis?
No, I'm just gonna so what we will just do is we'll just take these set of vectors that we have, and we are going to just use an orthogonal set. That's all. Okay? Because trying to find the metric on CFTs or some field theories is not that simple thing to do.
Inner product, the matrix inner product of psi.
Yeah.
So psi I
Yeah.
J,
Sure.
and use that as and then invert that and use that as a
Okay. Yeah.
matrix.
Yeah. Sure. This is a straightforward thing, but I just was we were just not clear about what exactly was happening here. Why it was going through in a simple way for say the CFT case. Okay. You're just saying that. Okay, yeah. Sure. Good. Yeah. So if you have for example degeneracies out here, then it just the whole thing just goes through in the sense that you could work with this particular the trace prime and the trace at the end of the day would be the same. Okay, so this is a slide. Yeah, since it's clear to all people out here, then I'll just skip this. And so what we are going to be doing is we are just going to be trying to use an orthogonal set for the BMS. Okay, so so you have so you want to find out the trace of this particular operator, and we want to do it say level by level, and in order to do this, so we're going to look at this psi 1 and psi 2 instead of just looking at L minus 1 and L m minus 1 at the first level. You also look at
Usually in the character you don't
That's right. That's right. That's right. Yes. But I mean, the sort of regime that we are looking at will not be. So we would not have. I mean that particular effect out here, actually. So we are. This is yeah. So we are looking at. Okay, let's just I mean move ahead here, and I mean let me show you that this works. And I do agree that the null states are an important part of the analysis, and you should mod them out as well. But for the moment, let's just go ahead without looking at null states. So what you do is you find you sort of use an orthogonal basis, and you get that psi1 and psi2 are these states that you have to do. And the norm trace at this level would mean that you have some factors in front and a 2, which sort of gives a counting of states at this level. Okay, so you can do this for level 2. You will have 5 states here, and you have to orthogonalize these 5 states, and this is again yeah. So you're saying that one could just use the. Yeah, I mean the point essentially is that the metric. I'm not. So there are zeros as well. No. I'm saying that there are zeros which are not null states. So things like if you have something like mn on some phi. This is, this has a zero norm, but this is not a null state, right? If you have something like this, then this is not zero. A null state is something that is orthogonal to everything in the Hilbert space, including itself, not just a zero norm state. No. I'm not speaking about spurious states. I'm speaking about null states.
So if you have a state which has zero norm,
yes.
are you going to count it or not?
Yes.
If you are going to count
yes. Yes.
In usual cases, you don't you just mod out those things. You don't want to mod them out.
No. Yes. Yes.
Usually when you say null state, it's also orthogonal to everything, right? Yeah, but so
this is not.
The way to do that is compute the matrix.
Yeah.
And look at the zero eigenvalues, not the zero entries in the matrix, not the zeros on the diagonal.
Sure.
Eigenvalues. But in general, for generic values, if you ignore the possibility of by null state, when you diagonalize the matrix, whether the eigenvalue is zero, not whether the diagonal entry is zero.
Okay.
Right?
Yes.
So now, if you take the point of view that you are working with generic central charges, so you don't encounter null states, you just use that matrix.
Yeah.
Even though you have zeros in the diagonal, you can invert it because there's no zeros in the eigenvalues, and then use that to construct.
Okay. Yeah. Okay. So that's okay. So the reason why we took this detour is because that was I guess one needs to prove that you will not get any zeros when you're trying to.
Depending on if you tune your delta charges in such a way that you can engineer an eigenvalue which is zero. So that's
okay. Yeah. So yes. So the
have null states in the beginning.
Right.
Everything was scaling, right? You start with something which has a null state, that thing, then scale and see if that is already a null state or not.
No, but if you just want to do it everything in the beginning
You can do that.
then you can just
so the point is that if you were to try to get the cat denominator without knowing, say what suppose now you start off with some given symmetry, which has no relation to what limits you take at the end of the day. Then trying to get at the cat determinant is non-trivial, right?
But you have your algebra.
Right.
You have your algebra, and once you construct states like so.
Yes.
And using that, you can
compute inner product between all 5 states.
Sure, 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 sure.
Without any input, right? You just
Yeah,
leave
yeah,
the
yeah.
deltas in the side.
Right, right.
So you have a bunch of functions like that, and then you want to take its inverse and see where the zeros are.
Okay. I mean, the
Maybe
thing
that's
that I'm
not what
trying to say, no, I mean, it would, I think, give me the same things at the end of the day. Trying to take the limit, is a simpler thing to do here.
No,
But you're saying that you could explicitly do that.
Yeah.
Okay, okay, true.
And then
Okay.
see whether you get
Okay,
the
okay.
interesting question in this context would be whether there are null states which do not come from the limit. I don't know.
No, they don't. I mean,
That's possible.
so that's an answer that I can give you. So yeah, we don't have such extra null states. Okay, so the point essentially is, so you could write down what the form of these guys are, and you could write down again. So let me get, so this is again reasonably just so what you get is you get these highest weight, expressions for the highest weight characters of the BMS. So we use this orthogonal basis to get this down, and this is of a nice form. So you have, so if you write it in terms of of the eta function, you could you have a certain form of this, and the vacuum character has is the one where you put so L minus 1 and M minus 1 acting on this will be 0. So this is going to be slightly different, and so to get the Z BMS, you just sum over all of these guys, and that is what you have at the end of the day. So this is sum over the, so this is what the BMS highest weight characters are.
These characters can also be obtained from the one.
Yeah, so I'll show you how to go about trying to. So you're saying just a saddle. So you can obviously look at a limit of what you had earlier and reproduce that. But you're saying a saddle point like analysis on the Villars over characters. Yeah. Yes. Yes.
Now you're getting one.
Yeah. So I'll just show you that. But again, so I think I have overshot by a long way. So let me try and get to something. So I'll skip this for the moment and go ahead. So what you can do is you can start off by, so okay, it's a little hard to just wrap up like this. Okay, so all right, let me just get back here for a second. So there are these two ways of trying to take the limit, which yields the same answer at the end of the day. Okay, so this is the part where I was trying to say that there is going to be some things that I do not understand, and so this is the one that I spoke to you about earlier, where you can take this limit and just go from here to here. There is also another limit where you recombine things in a way that is ln plus L bar n and ln minus L bar n. Just notice that there are no mixing of plus and minus modes in this limit. So if you just write down the vector fields form of these, you'll see that these are just interchanged by an interchange of sigma and tau. So it's clear why these are giving the same limit. Yeah, so this is, so the thing that I wanted to say out here is that this sort of non-relativistic limit, where you are not mixing up modes, maps, these say the Virasoro primaries to BMS primaries. Okay, so the highest weight representations map to highest weight representations, And this forms a useful tool to check some of the answers, that you have got by doing this, intrinsic highest weight analysis. So you can put these C's and H's in, and then you can just check what what the limit does to you. So you start off with chi bar. You put all of these things in that I mentioned in the last slide, and you take the limit, and you get back the answer that we had earlier. So this answer matches with the previous analysis. Yes. Yes. And yeah. Yes. Yes. So you just explicitly write this down, and yeah. Now, you can also do the other limit, the thing that I was doing so far, and this actually again gives you the same answer. Okay. Now, if you're looking at the representations that arise of this, other limit, these are clearly not highest weight representations. Now, the reason why these are not highest weight representations is that if you were to look at, ln, psi, and L bar, and psi acting on 0, instead of having, the BMS highest weight representations were, the highest weight representations were ln acting on phi equal to 0, and n acting on phi equal to 0 for all n, greater than 0. And these ones, which are these induced representations, these are all mn's acting on phi equal to 0 for all n's not equal to 0. So these have been looked at by Glenn and Blaja, and the expressions for the characters found using Frobenius method and all explicitly matches this. Okay? Yes, yes. As I was saying, the highest weight representations are explicitly non-unitary. So you can look at this matrix, and you can see that the determinant is minus xi squared. So these have to be, for any xi which is not equal to 0, these are non-unitary. On the other hand, the xi is where h minus h bar, right? H and h bar were both real to start off with.
Certainly, highest weight representations in this
Yeah.
Are some very weird ones.
Yes, yes.
Some very weird ones in this stuff.
Yes. So, but on the other hand, these guys are sort of limits of unitary representations. They look very weird. They are, you can't do much with them, but at least the character is something that you can find out. But the characters in both the cases are the same. So there is no earthly reason why these two very different representations should have the same character, but they do. And this sort of non-relativistic, ultra-relativistic play-up is happening all throughout in these, three-dimensional case, three-dimensional bulk, two-dimensional boundary case. We have been able to reproduce a lot of stuff using things in highest weight representations. Maybe it's all going through because similar things happen in the ADS case and they're just following through. Maybe there's something deeper at play in this, interplay between the two things. We do not understand this. So this is no. So the highest weight representations, as I said, are non-unitary. The induced representation, the selling point of the induced representation is that they are supposed to be unitary. because you can't do much with them at all, but at least saying that it's, I mean, unitary, you know.
No, I'm talking about the different algebra elements.
Yeah. So one of them gets you to the highest weight, one gets you to the induced. Okay?
Why are you saying that you can't do many things with them? What are the things that you can't do with them?
What? So the only thing that people have actually done with them is this. Actually, I mean, try to compute what the characters are. So the other checks and things that we have, you know, I mean, as I showed you one thing about the, way of counting states and so on, that sort of implicitly, assumes that you're looking at highest weight representations. Maybe that information is being washed away somewhere. Maybe but you know, say, so we've been trying to look at, I showed you about things about thermal entropy. We've done similar things, about entanglement entropy and so on and so forth, which explicitly uses highest weight representations. And there are, many ways to check that the answers that we have got are right. So there is something maybe deeper at play which we do not understand, but let me just, okay. So what we have done, finally to wrap up, is that, so the BMS field theories are putatively dual to, asymptotically flat spacetimes. We've looked at the notion of modular invariance in 2D BMS field theories. This helped derive the Cardy-like formula for these and flat space cosmology solutions in three-dimensional Minkowski space. So we discussed them, and we saw that these have a cosmological horizon. This can be viewed as a limit of a BDZ. And we saw that we could do a Cardy-like counting in the dual field theory to reproduce this Bekenstein-Hawking entropy of these LSEs. What we tried to do in the, later on is that we tried to construct these characters of the BMS-3 algebra. So we needed to define the notion of trace, and we built this orthogonal set of basis vectors. Maybe this was an overkill. We could have just used the metric. We could have just used the inner product metric and inverted it. So the trace gave rise to the highest weight characters of the BMS, which were then reproduced as a limit from the Virasoro case. And we saw that the highest weight character and the character of these induced representations gave identical answers, and we were at a loss of trying to explain this. So there are several things that we want to do on this. Understand, first of all, what on earth is going on with these two representations. We want to extend this to super BMS theories, theories of higher spins, which we call BMW theories, if you So Glenn and Alex Manoni, Gonzalez, and Oblak have also done a gravitational one-loop partition function analysis, and this matches with the BMS vacuum character. We could try and generalize this for these other theories as well. We are trying to actually use modular invariance to constrain BMS theories, so this is work in progress. And I'm not going to say anything about the last bit, because I'm already at 2 hours, I think. So thank you very much.
Questions, ICTS?
Everybody is hungry, it seems.
ICTS questions?
No.
No questions, no more questions.
So perhaps we can have a discussion point.
Sure. Yeah. Thank you.
Let's thank Arjun again.